Good morning everyone, and welcome to today's worked exam answer video. Today's question is all about how transition metals can be used as catalysts in different reactions, and as with a lot of the inorganic content, I'm going to show you how the answers to all of these questions are things that you can rote learn and thus recall immediately from your memory in the exam. There is absolutely no application of knowledge and understanding in any of these questions. It is quite simply learning definitions, equations and facts about a couple of different reactions. So these are the sorts of questions that we ought to be banking the marks on. I appreciate if you find it difficult to commit information to memory, that these sorts of questions might not be your cup of tea, but I would strongly encourage you to do all you can with flashcards or posters, or by recording yourself saying the facts, which you can then play back to yourself, or having them stuck up around your room or in places that you frequently visit in the house, because we can just recall information for these questions, as I will show you now. Okay, so the first question is we're asked to state the general property of the transition metals that allows the vanadium in vanadium 5 oxide to act as a catalyst in the contact process. Now we do need to know the general properties of the transition metals more widely, so they form complexes, have coloured ions, have an incomplete d sublevel, and in this instance the thing that makes them great catalysts is they have variable oxidation states. And as you'll be able to see in both the equations for part B and down here in part D, we are changing the oxidation state of the transition metal in those reactions. So the first one we're asked to show is the equations for how vanadium 5 oxide acts as a catalyst in the contact process. So the contact process is when we take SO2, react it with oxygen to make SO3, and this SO3 is then used in the manufacture of sulfuric acid. The vanadium initially is in the +5 oxidation state, which is what the 5 in brackets there means, the 5 being in Roman numerals. And then we change it down to an oxidation state of +4. However, because the catalyst has to be reformed, in the second step we need to return the vanadium to its +5 oxidation state. And catalysts and all intermediates should cancel out when you then write your overall equation for the reaction. Because they're catalysts, they can't be changed permanently, they therefore shouldn't appear in the overall equation. So those are equations you have to learn. Likewise, there are a number of definitions in this topic that we have to learn. One of them is heterogeneous, which means that the catalyst is in a different phase to the reactants. So the reactants are gases and the vanadium 5 oxide is a solid. Now, if we have impurities within the reactants, that causes a problem when we use the vanadium oxide as a heterogeneous catalyst in this way, because the impurities might poison the catalyst, and they would do that by binding to its surface. Heterogeneous catalysts often work by having these reactant gas particles temporarily adsorbing onto the surface. This weakens the bonds in the reactants, and then when the products are made, they desorb from the surface. If the surface is filled with the impurity, then the catalyst is unable to work, and we would say that the catalyst has been poisoned. Then we've got another reaction involving a different transition metal ion. It's a reaction between C2O42- ions and an MnO4- ion in acidic solution, and we have to understand that this is autocatalyzed. We need to first of all know what that means. This is another definition. So autocatalyzed reactions are reactions that are catalyzed by one of the products that is actually made in the reaction. So we're not adding a separate catalyst like we did for the contact process. We are making the catalyst within the reaction, and then as soon as it's made, that then speeds up the remainder of the reaction. And in this reaction we make Mn2+ ions, and they are the autocatalyst because they will change their oxidation state up to +3, and then we'll reform them back in the +2 oxidation state. And what that enables us to do is first of all deal with this negative MnO4- ion, and then the intermediate Mn3+ ions can deal with the oxidation of the C2O42- ions to CO2. And again, when we combine this together, we'd have to cancel out all of the intermediates. It's a little bit different because we can't lose all of the catalyst because some of that catalyst is made as a product. So the moles that are acting purely as a catalyst should cancel out, but there should still be some Mn2 on the right hand side of our overall equation because it is still a product in the reaction, and that's the slight difference with an autocatalyst. But again, those equations, we must learn them. Now, you may be able to piece them together if you can remember parts of what's going on. So if you can remember the overall equation for the contact process, you know that vanadium 5 oxide is what we start with, you might be able to work those out instead of having to rote learn everything. I think that's a little bit harder to do with this example because there is a lot of charges and different balancing numbers to contend with. So I would probably recommend definitely rote learning this one, but you might be able to piece that one together. But all of that information comes up time and time again in questions like this. So definitely get some flashcards or posters made of this, or get some recordings made that you can listen to, or stick some key points on your fridge, or whatever works for you. But that information is going to be really key to be able to draw upon in the exam. So hopefully that's been helpful. Any questions, as always, please hit me up on the comments of this video or through social media or via email, because I'm always happy to help. Hope you have a good day, guys.